Okay, now let's talk about energy. So in this course, energy is the ability to do work or the amount of work that must be done on a moving object to bring it to rest. And we'll also outline mechanical energy, which is what we'll focus on in this course since it's a mechanics course. So I'll give you three different forms of mechanical energy, which is it's just a form of energy which can readily be converted from one state to another, as you'll see later on. Um, so energy is the ability to do work. So let's consider a ball up here. Let's say we have this ball, and let's say we have the ground down below here, and let's say that this is where height is equal to 0. So we often refer to this as like a datum, which is a reference plane, where we have a height equal to 0 there. A common datum that is used is like mean sea level. If you give the elevation of say, a mountain or something like that, then this elevation is given above mean sea level. So it's a reference datum here. So that's where our height is equal to 0. And let's say that this ball is positioned some distance above our datum. We'll just say it's positioned up here at h. And the forces that act on this ball, well, if it's in free fall, we'll ignore wind resistance and all that right now. So the only force acting on it will be the weight, right? So this is the gravitational force. And so if we consider, energy is the ability to do work, let's take a look at how much work gravity could do on this ball. So the work done by gravity on the ball would be equal to the gravitational force times how far this could actually fall, right? And this distance it falls, h, or this displacement is parallel to the force, right? The force is downwards, the displacement would be downwards as well. And so this would be the work done by gravity on the ball. And they're the same direction, so this is positive here. But our gravitational force, this should be a capital F, this is mg, right? So the work done by gravity on the ball would be equal to mgh. This is our gravitational force right here times the displacement of it, and so this is mgh. So since this is the amount of work that gravity can do on the ball, and energy is the ability to do work, then how much energy this has, how much work it could potentially do, is mgh. So we call this our gravitational potential energy, so PE grav. Oftentimes potential energy is written with a U as well, so this is U grav. So gravitational potential energy is mgh, where h is the distance it can fall and mg is its weight, so it's a force applied through a distance. So this is our gravitational potential energy. Two other forms of mechanical energy that we'll give here are, well, we have a spring. So let's say that we were to compress a spring. We know that the force the spring exerts on the object is equal to kx, the magnitude of that force. And so if we kind of look back at our previous video, if we were to plot the force and the compression or the stretching, doesn't actually matter. The magnitude of the force would be the same regardless if we compress it or stretch it. If we were to plot these, then we know that the area under the curve would be the work, right? And so how much work is done must be how much energy is stored up. If we were to compress it and then release it, then that's how much work it could do when it's released. And so the area under the curve would be, well, if this is F is equal to kx, then the area of this triangle here, if this is linear, the slope is k, then the area is 1/2 kx squared. And so the amount of energy stored in a spring is the amount of work that a spring could do on an object. So here's our spring, and it's compressed some distance. So let's say the uncompressed distance was out to here. So our compression was x, this much right here. So then how much work it could do, the work done by the spring would be equal to this area down here. This is 1/2 kx squared, where k is our spring constant. And so since that's how much work could be done by the spring, that's how much energy is stored in the spring. So we say this is our elastic potential energy. So PE for elastic, or we have U elastic. This is equal to 1/2 times the spring constant times the compression or the stretching squared, 1/2 kx squared. Very similar. I won't go through the derivation, but we also have kinetic energy. This is the energy associated with an object in motion. So kinetic energy, just like we had kinetic friction was the friction of things moving. Kinetic energy is the energy of things moving. Oops, I apologize. This is kinetic energy. The kinetic energy, or KE, or sometimes this is EK, this is equal to 1/2 of the mass times the speed of the object squared, so 1/2 mv squared. So there's our kinetic energy. And so we have our different forms of energy. We have U grav is equal to mgh. U elastic is equal to 1/2 kx squared, and kinetic energy is equal to 1/2 mv squared. And this is the speed. This is the speed of the object. And this is the compression or the stretching. So these are always squared values, and the speed can never be negative anyway. So kinetic energy is always positive. Elastic potential energy is always positive. Gravitational potential energy is also always positive, because the distance it falls is the same as the direction of the force. And so energy is always a positive value. You can't have negative energy. We can have negative work, or positive work, but energy is always positive. Now we can have negative changes in energy, but energy itself, we can only have positive values. The sum of all these, if we put them together, this is what we refer to as mechanical energy. Or sometimes we just write ME, or sometimes we'll say this is our total energy. Total energy, which would be just, we say TE, the total mechanical energy. And so we have the mechanical energy, ME is the same as the total energy. So this is equal to mgh, our gravitational potential, plus elastic potential, 1/2 kx squared, plus kinetic, which is 1/2 mv squared. There's the total mechanical energy of an object. So it has to do with both with where it's located. Our potential energy is where it's located, or if it's a spring or a rubber band compressed or stretched, and also how fast it's moving. And all of these, like I said previously, mechanical energy can readily change from one to another. Let's say we go back up to the spring. When it was at rest, it wasn't moving. It didn't have any kinetic energy, but it did have elastic potential. Once it got fully decompressed, it didn't have any more elastic potential, but that elastic potential now became kinetic. So it very readily converted between kinetic and elastic potential. Same thing up here. We have, if it's not moving up here, there's no kinetic energy. And at the bottom, it has no more potential energy, but now it has kinetic. So it's readily converts between these forms. One last thing to kind of take a look at here, just these are squared values. So if I double x, if I go from x to 2x. So if I compress twice the distance or stretch twice the distance, then our elastic potential energy would go to, well, this is going to be 1/2 k times 2x squared. So this would actually be 4 times our elastic potential energy. Same thing is true with the kinetic down here. If I go from just a speed to twice the speed, then I go from just a kinetic energy to 4 times that kinetic energy, because this is squared. So something to pay attention to with our proportional reasoning there. But anyways, these are all of our forms of mechanical energy that we'll deal with in this course.